Hello everyone, welcome to this video series in which we are developing a value at risk model using the variance covariance method, historical simulation method, and the Monte Carlo method. So in the last video, I have covered the theoretical aspect of how do we develop a value at risk model using the Monte Carlo method. So if you have not seen the theoretical video, I highly recommend you to watch it. And in this video, I'll be helping you with understanding how to develop the value at risk using Monte Carlo in Excel. So, one disclaimer which I wanted to give you is I have seen a lot of videos in which people do teach how to develop value at risk in using Monte Carlo on YouTube. And the way they do is they generate random probabilities, and using those probabilities, they try to calculate the value at risk number. So, I did discuss this methodology, what I'm presenting to you with my professors. So I'm very sure that this is how, I mean, at least in academia it is done and not the other way around what you see on YouTube. So, so I'll just walk you through these steps. And also this method I've spoken with a lot of fellow quants and professor, and then that's why I'm very confident on what I'm showing you, at least from academia perspective. Okay, so let me walk you through the process. So the first step of, as we know, like the first step is to get the data. So assuming like we have three stocks in our portfolio, that is JP Morgan, Morgan Stanley, and Bank of America, we can download the data from Yahoo Finance, right? So the first step is to calculate the returns. So to calculate the returns, I have just used the logarithm, that is logarithm of today's price by yesterday's price. So I have used like the same formula all over for JP Morgan, Morgan Stanley, and Bank of America. And using this formula, I have dragged on the same formula till the end so that we can calculate the returns, the daily returns of our stock. So, the question is, how do we use the value at risk for Monte Carlo, right? So the main component of this whole Monte Carlo method is using the geometric Brownian motion. So basically, we are trying to use, or let's say we are trying to model the stock prices using the geometric Brownian motion. And please, I'm letting you know, this is like the most important step. Okay. So you might be thinking, what is a geometric Brownian motion, right? So geometric Brownian motion is nothing but a mathematical equation which is used to describe the, random behavior of the stock, or let's say the stochastic behavior of the stock. So it is mostly used in quantitative finance to simulate the stock prices. Okay. So if you see this equation, right? If you see this equation has three main variables. If you see, which is mu, which is nothing but your drift term, sigma is nothing but your standard deviation, and WT is nothing but your Wiener process, or it is also called the Brownian motion. So if you have not seen my theoretical video on Monte Carlo, I highly suggest you to watch that, because in that I have tell a lot about what is Wiener process or what is the Brownian motion, right? So so basically, if you see S naught is nothing but our stock price. Okay. So let's say if we are modeling our stock today, so S naught will be the yesterday's price. Okay. So S naught is our last price that we have for our stock. Mu is your drift, sigma is your okay. So coming on mu, right? Drift is what, right? So drift is nothing but your expected average return of the stock. Okay. So drift is, if you see this mu term, this is nothing but your expected average return of the stock. Sigma is nothing but, as we know, the standard deviation. WT is the Wiener process or the Brownian motion, and T is nothing but your time. Okay. So, so, so the first, so basically what we are trying to do is we are trying to use this geometric Brownian motion to model the stock prices. And how we are doing for the first step in this process will be generating the Wiener process, or we can say generating the uncorrelated random variable. You might be thinking, why are we, why this Wiener process or WT term is included in this whole equation, right? Or let's say why we are WT, which is also called, the random variable. Why we are including this random variable, or why there is a need to generate the random variable. Right. So if you see, the world of stocks, right? Stocks generally have random fluctuations. If you see the prices of the stocks, they have random fluctuations. And why are these random fluctuations? They can happen because of market sentiments, or let's say any market events, any financial news that you see around, or it can be because of any unpredictable factors, right? So, so what's, so why we are, generating it? Because we just want to add a randomness in the stock prices, because we assume that, the stock price can move and can, have some random nature or random fluctuation. So that's why we are trying to incorporate those random fluctuation in the stock price, and that's why we are using this Wiener process, WT. So the process is how to, you might be thinking, how can we generate the uncorrelated random variable? So if you have seen my theoretical video, what we are how the way we generate the uncorrelated random variable is using is using normal distribution. So what we are doing is we are using this formula to generate the normally distributed uncorrelated random variable. Okay. So right now, if you see in this box, you will not see this formula, because what happens is once you use this formula, the values, keep on changing, right? So I've just fixed it as of now. So what I'm doing is, see, because we have three stocks in our portfolio, so we'll have, three equation, right? S1, S2, S3, because we are trying to model all the three stock prices. So because we have three S1, S2, we have three equation, right? S1, S2, S3. That's why we'll have three Wiener processes, W1, W2, W3. So we'll use the same formula, right, all across, to generate the uncorrelated random variable and just drag down the formula. See, the concept of Monte Carlo, you might be thinking, right? So we are generating thousand simulations, and that's where the concept of Monte Carlo comes into place. So we are generating we are generating thousand uncorrelated random variable. Okay. So this will generate for each stock. So one thing which I really want to focus on is, I mean, we do not just use uncorrelated random variable, right? We have to use the correlated random variable. And why is that? I'll tell you why. See, if you see the portfolio, which is JP Morgan, Morgan Stanley, and Bank of America, right? They'll have certain correlation because they all belong to the financial industry, right? So they'll have certain correlation, or certain amount of, one stock will can influence other by some little amount, right? Or let's say we can say there's some correlation between, different stocks in the financial industry, right? So that's why we cannot use these uncorrelated random variables. So what we have to do is we have to generate the correlated random variables, which means it should have certain correlation between the stocks, right? So you might be thinking, why to generate the correlated random variables? So if we see in finance, it is crucial to model the correlation between different stocks, right? So if you see asset prices, or let's say stock prices, often move together or in opposite direction due to market condition, economic factor, or any other unpredictable factors. So if we just ignore this correlation, so let's say if we do not take into consideration the correlation factor, we are not gonna model the stock prices correctly. So to make sure we are correctly modeling the stock prices, we have to include the correlation term. How will we include it? Is by generating a correlated random variable and not using the uncorrelated random variable. So what is the process of generating the correlated random variable? So the process is, once you generate the uncorrelated random variable, you need to generate the correlation matrix. Using that correlation matrix, generate the Cholesky decomposition matrix, and then from Cholesky decomposition matrix, you calculate the correlated normally distributed. You can say correlated random variable, which are normally distributed. So let me walk you through the process. Okay. So first, if you see this, we have already done, that is generate the normally distributed uncorrelated random variable. How we have done is by using this formula, right? So use this formula all across to generate the uncorrelated random variable, which are normally distributed, right? So now let's calculate. So the second step is, if you see, calculate the correlation matrix. So how we are gonna calculate the correlation matrix is, I'll just show you. Go on data analysis, go on correlation, press OK. And once you press OK, so okay, so just just select this range of returns that you have, right? Just select this range of returns that you have, and let's say the output range, right? Let's select the output range to be, let's say, somewhere here, right? Let's say somewhere here, or let's say here, and then press OK. So just as simple as we have selected the the log returns that we have. If you see this part, we have selected the log returns, and then we are just calculating our correlation matrix. Just press OK, and if you see, our correlation matrix is there. I just need to put JP Morgan, Morgan Stanley, and Bank of America in the similar fashion, right? So I've just incorporated this. Now, if you see, the way you need to if you see, there are certain elements which are missing, right? So the way you have to fill is, it's very simple, right? Just do this and just take a transpose of this. Just take a transpose of this. That's it. So you can copy paste the same item here. So if you see this, this is what the correlation between Morgan Stanley and JP Morgan. So if you see, the correlation between JP Morgan and Morgan Stanley is 0.66, or you can say 0.67, which is the same, right? Similarly, the correlation, if you see, it's nothing but the correlation between JP Morgan and Bank of America. So if you see, it's JP Morgan, Bank of America correlation is 0.82, which is here, and then we'll fill this. So this is nothing but the correlation between Bank of America and Morgan Stanley, which is this member. So we'll just copy paste this, right? And see, so what we'll do is we'll just put it to two decimal places for better clarity. I mean, for better readability. So if you see this correlation matrix and what I have listed here, it's just the same, right? It's just the same. So let me remove this correlation. So now we have generated our correlation matrix. So now we need to, so basically now using this correlation, we need to calculate the Cholesky decomposition matrix. So in here, I have not written the formula. If you have seen my theoretical video, I have clearly specified how do we calculate the Cholesky, what, like, basically from the formula perspective, what are the formulas that we are using to calculate the, basically the how we are calculating the Cholesky decomposition using the correlation matrix. So this is nothing but your square root of, the first element that you have in your correlation matrix. Similarly, also one thing which I want you to understand is, in the Cholesky decomposition matrix, right? The upper triangular matrix is always zero. So you'll have values in the lower triangular matrix. Okay, if you see this, so this is nothing but your lower triangular matrix. So your upper triangular matrix will always remain zero. So this is nothing but your square root of your first element. Similarly, if you see this, this is nothing but you take into consideration the second element here, which is, and then you divide it by the first component you calculated for the Cholesky decomposition matrix. Similarly, if you see this, this is nothing but your square root of A011, which is this value, and minus AN16 square, which is this value. And similarly, you'll calculate this, which is nothing but AN12 by AN15, which is this by this, right? And similarly, you'll calculate. So this is just a way of calculating the Cholesky decomposition matrix, right? So basically, from correlation matrix, we are trying to calculate the Cholesky decomposition matrix. So one question you might be thinking, right? I mean, Mehul, what if we have 50, let's say 50 stocks in our portfolio? I mean, calculating the formulas becomes so tough, right? For 50, let's say, or 100 equities or 100 stocks in the portfolio, right? See, the thing is, all this modeling, right? In the industry, they are done in Python. So Python has a very simple function of Cholesky decomposition. Basically, even if you have like what should I say? Even if you have, let's say, 100 portfolio or 100 stocks in your portfolio, you can still calculate this whole thing very easily. You can still calculate the Cholesky decomposition matrix very easily. Python just has one line of code for the Cholesky decomposition. So it basically takes into consideration the correlation matrix. So once you get the correlation matrix, it will automatically give you the Cholesky decomposition. So don't worry on the formula because it's pretty much done in Python. All this modeling is done in Python, right? I'm just showing you in Excel because it becomes very easy to understand and visualize in Excel. So now the next thing is, if you see, so you got this Cholesky decomposition matrix, right? So you might be thinking, I mean, how can I be sure that my Cholesky decomposition matrix is correct? So what you can do is, if you multiply this Cholesky decomposition matrix with the transpose of this whole matrix, you'll get the correlation matrix. So if you see here, what I've done is I've multiplied m mult is nothing but a matrix multiplication of AN15 to AP17, which is nothing but your Cholesky decomposition with your transpose of Cholesky decomposition. So you are just matrix multiplying it, and you basically a matrix multiplication, and what you'll get is your correlation matrix. So after you get your correlation matrix, as I said, right, once you get your, sorry. So okay, this is just to confirm, right? I mean, this is just to confirm what you have. If you see this and this, it's exactly the same, which means yes, this Cholesky decomposition matrix is correct. So once you get this Cholesky decomposition matrix, the next step is to calculate the correlated random variable. So you might be thinking, how to calculate the correlated random variable. So the process is fairly simple. So I mean, what you need to do is you need to multiply, AN15 to AP17, which is nothing but your Cholesky decomposition matrix, with the transpose of your uncorrelated random variable. If you see here, which is Q16 to S1005, this is nothing but your whole, this is nothing but your whole uncorrelated random variable. So you just need to matrix multiply these two, right? You just need to matrix multiply, and then you just need to take the transpose to get the correlated random variable. So I've used the same formula all across, right? So if you see, I've just used the same formula all across to generate the correlated random variable. So how we are doing is, we are just multiplying the Cholesky decomposition matrix with the transpose of the uncorrelated random variable to make it visualize you better, right? So what we are essentially doing is, if you see here, right, this, okay, I have said taken the first three row as an example, just to show you how we are calculating. So what we are doing is, we are taking the first uncorrelated random variable w1 and multiplying it with this. Okay, so essentially what we are doing is, we are taking, if you we are taking the sum product of this with this. Okay, so it will give you 0.9, 0.942, right? Similarly, what we are doing, how we are calculating this is, we are taking the sum product, right, of this, again this, with this, right? So essentially what we are doing here is, okay, so just to clarify, what we are doing here is, we are multiplying W1 with just 1, right? So we'll get 0.942, if you see, right? And then for this, what we are doing, if you see this value, what we are doing here is, we are multiplying W1 with 0.67, and then adding it with W2 multiplied by 0.74, right? So this is how we calculate this. So if you see, either you can do some product, which I find it little easy, or you can, basically multiply each and every term. So if we say this will also give you the same value. Okay, so if you see 0.934, right? Here I've done some product. I feel like some product is fairly easy. And if you see here, what I'm doing is, I'm multiplying W1 with JPM, W2 with Morgan Stanley, W3 with BAC. So this is how, we are using Cholesky decomposition matrix and multiplying it with the uncorrelated random variable to calculate the correlated random variable. So similarly, if you see this, we are doing nothing but we are multiplying this with this, or you can also say, you can also say, like, we are doing the sum product of this whole with, this. this thing. So this is nothing but we get the same thing, right? Point negative of 0.567. Similarly, here if you see, I mean, what we are doing is we are just multiplying, these two term with these two, and then for W3 we are multiplying everything with everything. So either you can use, if you see, I can also use some product, right? So if you see, I have just used some product this with, it's just the same. I mean, it's just the same. I mean, you'll get the same values. So if you see negative of 0.061 or this, which is like just the same. So similarly, you'll use the similar formulas to calculate the correlated random variable from from the uncorrelated using the Cholesky decomposition. Whoa, now we have this WT term. If you see this equation, now we have this WT term, right? So what is left? S naught is left, mu is left, sigma is left, T is left, right? S naught. What is S naught? So let's say if we have the price, right? If we see our data, the prices from 2022 to 2023. So the next day is nothing but 8/3/2023. And this is the day wherein we are calculating the value at risk number. Okay, this is the day in which we are finding the value at risk number. So what we have to do is S naught is nothing but your previous day value data. So if you see 157, 90.94, 31.36, this will be our S naught for all the three stocks that we have. So if you see, we have the similar 150. If you see here, S naught is nothing but 157, 90.94, and 31.36. Basically, what if we are trying to calculate tomorrow value at risk, we'll take today's value as S naught. Okay. So we have S naught calculated. Now the next term is mu. See, this mu term is nothing but your average return. We always consider, okay, average return as a risk-free rate. So I'm assuming, okay, so what I mean is we'll always take it as same. The drift term will always take it as same. So I can take the risk-free rate as, let's say, 5%, 4%, 3.5%, whatever the risk-free rate is, right? So so right now I'm considering my risk-free rate as 4%, which basically means that I'm expecting the average return. I'm expecting the return of this stock to be 4%. Similarly, I'm expecting the return of the Morgan Stanley stock to be 4%, and same for Bank of America. Now to calculate the volatility, we are simply using the function standard deviation dot sample, and we are just giving the returns. We are basically calculating the volatility from these returns. Okay. If you see, that's how we have calculated the standard deviation, or let's say the volatility. So now we have everything into place. We have S naught, we have drift, we have volatility. T is nothing but the simulations. Okay, one by, see, if we are taking 1,000 simulation, so T will be 1/1,000, 2/1,000, 3/1,000, right? And we have sigma, we have WT, so everything is in place. Now we'll be using this mathematical equation, which is the geometric Brownian motion, to model the stock prices. Okay. So if you see, what we are doing is S naught is nothing but your AN7, right? This value, this multiplied with the exponential of drift. Mu is nothing but your 4%. If you see this value is nothing but your 4% minus sigma square. If you see what is your sigma, 1.62, right? So here also, if you see, what we are taking is 1.62% or 0.0167, it's both the same. So you are squaring the standard deviation, dividing it by 2, and then if you see AR6 in this case will be 1, because as I said, it will roll 1, 2, 3, whatever time frame we are considering. And then again, sigma is nothing but our standard deviation. WT, right? In our case, now WT is nothing but your correlated random variable, W1, right? So this is how you'll model the stock price for JP Morgan. Similarly, you'll use the same formula. You'll use the same formula for for modeling the stock price for Morgan Stanley. Only thing which you have to consider is AD6, or let's say the WT in this case will be our W2, which is the correlated random variable for Morgan Stanley, right? So W1 is the correlated random variable for JP Morgan. W2 stands for the random variable, correlated random variable for Morgan Stanley. BAC is W3 is nothing but your correlated random variable for for Bank of America. So we'll be just using the same formula for calculating the stock price. So let's say for simulation two, if you see if you see AR7 becomes 2, right? AR7 becomes 2. And similarly, if you see here, the AR will use AR8, which is 3. So the T will revolve 1, 2, 3, up to it will go up till 1000. And we'll be using the same formula, to basically model the stock prices. So once we have simulated the stock prices using the geometric Brownian motion, and we have this assumption that we are, basically we have this weights, which is 30% we are investing in JP Morgan, 40% in Morgan Stanley, and another 30% in Bank of America. So what we are trying to do is, we are calculating the return of we are calculating the returns. Okay. So basically, okay, this is our assumption, right? So let's first calculate the individual stock returns, which is nothing but your logarithm of your current stock by previous stock price, right? So similarly, you'll be calculating the log return of JP Morgan, Morgan Stanley, and Bank of America. Okay, so you'll be using this formula to calculate the log returns. So once you have the log returns, right, or let's say once you have the returns in place, the next thing is to calculate the portfolio returns, right? So let me show you how to calculate the portfolio return. It is like fairly easy. What we are doing is we'll do the sum product, right? So we'll do the sum product of weights by this, right? And just enter it, and we'll use this formula to calculate the sum products. Okay. Okay. I guess I did not, I guess I need to, yeah, log this. So let me Okay, perfect. So this is how we calculate the returns of our portfolio. So, once we see, the thing is in the Monte Carlo method, right? The main component is to model the stock price using the geometric Brownian motion. Once it's calculated, now we follow the same historical method. That is, you take into consideration the returns, then you calculate the portfolio returns. Once you get your portfolio returns, just press Control Shift L to get this filter. Okay. So just arrange this in ascending order. Okay, just give me 1 second. Smallest to largest. Okay. So, okay, I guess there's some issue. I guess it did not went through because I can see. Okay, wait, yeah. So this is, let's say, our return, right? This is our return that we have calculated. So let's arrange this in ascending order from smallest to largest. I guess it's not happening for some reason. Maybe. Okay, I understood why it's not happening. Okay, so I need to, you know, make it first constant. Okay, yeah, so I have just removed the formula. Now let me do smallest to largest. Okay, perfect. So once we have this, right, this is nothing but our portfolio returns in ascending order, right? So if you see, this is nothing but, if you see, these values are just the same, right? So if you see any of these values, if you see these values are just the same. So what I did was I calculated the portfolio return and then arranged them in ascending order. So after I arrange them in ascending order, the process is very simple, right? So let's say if we have 999 days of data, right? Let's say. So what we are doing is we are just keeping, okay, let's say we are calculating the value at risk. Okay, so one correction here is, because we are doing thousands, okay, we are using thousand simulations, or we can keep, I guess, because the number of returns here is 999, right? Okay, so we can keep here is 999. Okay, perfect. Yeah, okay. So I guess the returns are 999. Okay. So basically, let's say if you are calculating the confidence interval at 99%, our alpha is 1%. So what we need to do is we need to multiply the 1% with the total number of days we have. So 1% with, so multiplying, let's say 1% with 999 gives you 9.99. Now, if you see, there is no such position as 9.99, so we'll basically round it off. So this becomes 10. And once it becomes 10, right, we just need to, I've just used a VLOOKUP to calculate what is my value at risk return at 10th position. So if you see at 10th position, it is nothing but negative 5.27. If you see this number, so I've just written negative 5.27 multiplied the value by the portfolio value, and that's how we get, the value, 1 day value at risk at 99% confidence interval. Similarly, let's calculate at 95% confidence interval. So alpha value will be 5%, multiplying 5% with the total number of data we have, which is 999. And so just rounding it off, and this becomes 50 because there is no such position as for 49.95. Using VLOOKUP to find what is the return at 50th position, which is negative 3.80. So this then multiplying, so this is our value at risk return at 95%. So to calculate the dollar value at risk, we are just multiplying the value at risk return with the portfolio value to calculate the value at risk, 1 day value at risk at 95% confidence interval. Similarly, for 90%, our alpha will be, alpha value is 10%, multiplying the 10% with 999 to get, the position, rounding up the position. So at 100, we need to find, okay, what is our return at 100 position, so which is negative 2.93. So we are just using negative 2.93 multiplying with the portfolio value to get the value at risk at this at 90% confidence interval. So let me summarize this method once again so that it's easy for you to understand. So the first step is of course to download the data. Second step is to calculate the returns of the data. We are trying to model the stock price using the geometric Brownian motion. So S naught is nothing but the initial stock price, mu is the drift, sigma is the volatility, T is the time, and WT is the Wiener process or the Brownian motion. See, because we know that the stocks are correlated, I mean, definitely, so we cannot use uncorrelated random variable. We have to generate the correlated random variable. So how will we generate the correlated random variable is by using the Cholesky decomposition matrix. So we get how we'll get the Cholesky is by using the correlation matrix. So first we calculate the correlation matrix, then we calculate the Cholesky decomposition matrix and multiply the Cholesky decomposition matrix with the uncorrelated random variables to get our correlated random variables. Now, once we get the correlated random variables, the whole process becomes easy because we have S naught, we have drift, we have calculated the volatility. T is nothing but your, simulation like 1 by 1000, 2 by 1000, right? And then we have WT, which is our correlated random variables. So once we calculate the stock price, right, we simulate the stock price using geometric Brownian motion. Then we calculate the returns. So once we calculate the returns, we then calculate the portfolio return basically by multiplying this with the weights we have, arranging them in ascending order. Once we arrange them in ascending order, depending on what confidence interval, right, we'll get our position, and we need to look at the value at risk at that specific position and multiply, we'll get the value at risk at that specific position and multiply it with the portfolio value to get the value at risk at that specific confidence interval. So that's all about this video. If you have any doubts, please do post it in the comment section. And I hope this video might have helped you. Thank you so much. And please let me know if you have any other doubts.